of two sides. In one side, we are getting a response to lower frequency, and in one side, we are getting a response from higher frequency. The whole we depend that side. Right? So when more, that means the subsurface is much more standard in case of your high frequency part. That means whenever you are getting a response at the high frequency, so that means it is a very shallow formation. So that means soil is very thin. And if it is a lower frequency, that means there is a considerable thickness of the soil on the bedrock. Okay? Any other questions from this?
So, kung was the stochastic, so I mean, I think it can be the same code, but as you said, people like saying different titles it does. Or I mean, like the VS30 that I bought, that was the 0.3 per line actually. But still, I have used like take my characters. The fit what in during the side character after HPSR, I took the side characterization. The side characterization, I got fundamental frequency. So I used that to also calculate PSR.
Okay.
I was also there. The other parameters like data bits, activation, I use all of those things. I was texting the script back into my team. So if some length on that, so I would produce the plots. But the key to on my that mine is very small. Okay, I enjoy using this.
Okay. So these were consideration that actually percent ratio, both hardware and sensor and short wave sensor immediate same response. So those hardware sensor exactly and one is short wave. So it's small. So the reason that saying we get the instrument because technically it shouldn't be it. I don't know, because it should have we probably put that on the inputs. And we should have used that let's say past doing same things. And when you carried out two different instruments, and they are when I identically placed to then different materials, and that is what we have tested this summer also. But if you put the sensor inside the meeting, and from the sensors in the outside, hearing additional means you cover the thermal SRAM called the instant room carrying effect as a printing effect of the coming incoming waves. And we'll also we have seen that if we put it onto the ground, just like most people accident to the columns, and when the sensor and put a to the bucket on the top kit just to invite them in the noise station. It means also beyond that vibrations, right? Then the frequency response will be distinct. More the better outside bomb show that show the noise in the wind, noise generated by the wind is also affecting the recorded signal, right? And so that's why also it will be creating some edge vessels where say at some high frequency will be different. Okay. So there are a lot of experiments you can do, and also if you have a site calculation for using the SSR technique, if we have a rock site, then it will be very interesting to see how it will be implemented in the study of the earthquake hazard at a particular city or particular urban environment, where the spatial variation of the site response is very important, because the soil type in the city might be different in different areas, and so the amplification will be the different at different places too. So that will be a very integral part of the of the side response. So what is this one?
Silk spray.
Huh?
So,
Oh, room spray. Oh, okay. Oh, yes. Yes, I said, yesterday when they said that, huh? So it's that things kiss that then that's why. If we just effect got the incidents come with this makes like so sometimes worrying we be that why that mistake that what is but when we take in by immediate when you have to start from the thing to the but to the end of the Israel end of the record you can do that things. Right but it even if they things that we don't even listen is an instant motion in that record you learn to so the energy of the P wave and with that and all the other way after that you will discuss on things that can window. It's always isn't that it's so therefore their contribution to the amplitude is not very significant. You can take and you can calculate the results of when because as that will be a good start to understand that. That take only the P wave 5 second or 10 second and do the P wave. You should not go for a 10 second because that way it will be encompass the other part of the wave. But if you just take the 5 second P waves and try to calculate the P wave when the ratio and then when I try to take the S wave and then try to take the after the S wave and see the results or take the full wave, take the results. It will be always interesting to see, but you will be seeing that the S wave part, so when the HVSR is more or less predominant than the other part of the waves. So because that's the highest motion in the recorded signal, okay, but that is the highest amplitude in the recorded signal. Then I get so it's such a show. Then we go let's doing preparing the pitch. So you saying to no in the in the in the micro in the ambient noise recording, what we typically do is this. If the record is not contaminated by any earthquake, because if suppose you are giving it for a recording for the ambient noise and in the time there is an earthquake has happened, then it will be difficult, okay, because we do not want that. We want the micro tremor so that it's basically the or might be the ambient noise because of the but we like to investigate the ambient noise. So what we typically do is this, that we take a record of something around 3 hours recording if it is uninterrupted by any earthquake. So after 3 hours of recording, we take the record and then we split that 3 hours into 1 minute of one window. Okay. And for each 1 minute window, we calculate HVSR. So then we calculate HVSR for all the 3 hours for it in that sense. So we have collected a lot of HVSR, say suppose 50, 60 HVSR for that window length, and then we calculate a logarithmic average of those HVSR and try to because the noise you do not know from where it is coming, and it's sometimes it is a directional noise is also involved because say suppose some car passed by, so that has created a noise, right? So we need to try to basically cancel all the random noise values and try to see which one is predominant in that sense. So the noise recording, we take a long window and then split the long window into few parts, and for each part we calculate HVSR and then superpose all the HVSR. together and take the average value and standard deviation. Right. So that way you can do that. And for the obtaining the amplification factor, it is specially told that for single station, it is difficult to get that maximum amplitude. So if you want to get the maximum amplitude at a particular set, the maximum amplitude, getting the maximum amplitude is not an issue. The issue is this, that to interpret which one you should take as a maximum amplitude, that is what you have to decide. Because sometimes when there is a small peak and then there is a big peak. Now, whether you will take the fundamental frequency associated with the small peak or the fundamental frequency associated with the big peak or the larger peak, that is a question always. Okay. And there is a rule book available. It is called Sesame Rule Book of the HVSR. It is ACA, Rules of Calculating HVSR and Interpretation of HVSR. So they had given some criteria on which you have to select which peak you need to choose, and what is the criteria of choosing that peak. So if you can Google that Sesame HVSR criteria, you will get some of the criteria about the selecting the amplitude and the fundamental frequency of a HVSR data. So if you can follow that rules, then you can find out all the amplitude and the frequency values very nicely. Okay. It depends upon how the bedrocks and the upper sediments are related. If the bedrock is very shallow, then what should be what deep bedrock, then what we should do. So there are a lot of criteria is there, and you can follow this criteria. Or if you want, I can show you some of the criteria we need to see for the HVSR peak. But that's the nitty-gritty. That's for your results and the interpretation of HVSR. And whenever you are going to do for a research work, these are the things you need to be careful about. But what I'm trying to say is that without complication, just to calculate first HVSR, try to understand which peak you are more eager to choose, and how much is the frequency values, and whether that frequency is related with the depth of the bedrock in that area or not. So if you have this much of idea in your first order picture, will be much more clear. Then we can have a lot of other criteria we can establish. Okay, so that's the things I like to emphasize here. Any other question?
Also, by cross-changing, we're going to after executing the stochastic one, almost 4 to 5 curves going to generate, and last one being this one spectra with the Gaussian. So, see, and I think that was, it was starting out in this generally the top pages, consider adding a show that it is on an end and then the setting things that are the must be support about after the acceleration generations, right? And then our generated the acceleration value. I have also calculated the velocity. I have also calculated the displacement. So right, so these 3 types of I am generated. So that was coming at phase A, B, D. And within this game pattern, the tech on the response picture, the case of it's an answer in it, is me, yes, me, and the ability values. This response spectrum has been generated. So it's really does to they sometimes be an anti-melee and as a response picture. So we need to know how to interpret that. So back my question down. You will change the magnitude, then you get change the distance, and then see while you're going by solution and all in this case are invading. So when that intel have a feeling that okay,
And for a second line to when we do not use that for why they're perceived that we think I be told him and should use or a trend that mentioned as there to guess this other producing at the same distance or not. So why do not that change? So in that in the distance, everything is okay. We added that. The GA also. You can do the 17 point the image going to be they have to make the object. It is the more language that image should be much smaller. Okay. So that you can generate and check it out with these things. Okay. 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 So let's see what we will do today is the brush. Basically the source type of analysis. It is a seismic source characterizations or seismic source when analysis for getting the recorded data. Okay. Now, we know that the basic part of the seismology or the basic part of this recording is this that the earthquake there is the created due to some force at the source, right? And this force we call it as a equivalent force, and that force equivalent has created a motion at the source, and from there the seismic wave actually coming up, and then it will be recorded. It will passes through the earth or the material of the earth, and then it is recorded at the recording station. So we are interested to give some mathematical formulation of this entire phenomena from the earthquake source to the recording. Now, and so as I said that these rocks are the elastic, has some elastic property, so it's the elastic body or elastic continuum. And in this elastic continuum, you know that our Newton's laws of motion is basically applicable. And if we assume that Ui is basically the okay. So this Ui is a displacement, right? So this is basically the displacement of the and tau is the stress. So that is your stress, and this is your displacement, and that is your internal force, and that is in the continuum, that's the internal force, which is the stress when it develops. Plus, there is a body force which is acted during the earthquake. So this is your stress changes, and this is your body force, right? Now, this body force, we need to solve these equations or try to write an equation which can solve these motions. Now, if I equals to 0, so that means if we assume that there is no body force, then this solution with this one, with this solution only, this will be given you basically the P wave and S wave formation, or basically the equation for the P wave and S wave. We will be discussing it afterwards. That's the P wave and S wave, how much they will be generated, what will be its velocity. That can be solved if I put the Fi equals to 0. That means there is no body motion. But if there is a body motion is there, then this equation is a little bit complicated equation, and we need to solve it. And not only we need to solve this part, but also whenever from the source, it will travel to the path through the material and recorded at the recording station. That also we need to compute, right? So basically, we need to calculate if there is a displacement at the fault, then how much will be the displacement created at the recording station. So that is what we have to calculate. Okay. Now, the displacement at the fault is created due to the application of the force. Now, so we are including a term which is basically we designate it as a Fx0 and T0. So please understand that Fx0 and T0, T0 is the time when earthquake has happened. So that means when the fault has ruptured that area, and X0 is the point where this rupture took place, right? So X0 and T0 are the origin point, right? In terms of the distance and in terms of the time, okay? And the displacement, you see this one, this is called uxt. So uxt is the displacement produced at a distance of x and at a time of t, right? So after some time t and some distance x, there is a displacement produced. Let us assume that is a uxt. So that uxt we have to calculate. Okay, so we need to know that values, right? So the uxt, beside the force generated at the source, this uxt function is also complicated by the Earth's seismic velocity and density of the material, right? So that is through which it is being passed, right? So that's will also come into the pictures, and also that since there is a stress part is involved, so there are various seismic phases, and the reverberation is also come into the pictures, right? So you will be getting say some sort of a P wave arrival, that displacement, S wave arrival, that displacement, any other wave phases, that displacement. We need to calculate all the displacement in order to find out what will be the recorded displacement at the recordings. Is it clear? This concept, the mathematical model is clear. So that means earthquake has happened, there is a force generated. Whenever there is force generated, there are internal stress is also there. So that will be generating the different wave phases, and all are being traveling through the earth, and then it will be all recorded at some distance, some time, and all the displacement will be summed up to give the actual recorded displacement at the recording site. Now, this recorded displacement, you can differentiate, calculate the velocity, you can differentiate, calculate the acceleration, and so on and so forth. So,
so for example, like how we say usually in the news also, it's splitting. Like for Africa, they say that been splitting. So in a similar way, can we kind of calculate how much is the grade?
Yeah, basically, if you have a recording station, and that recording station, and that is what basically we are not imposing that at the time the acceleration record, but might be the GPS signal is basically used to find out how much is the displacement produced due to this rifting and all these things. So that can be calculated. Yes. Okay. So UT or the displacement function, I just show you this displacement function. This is different from the various source to location geometry. So that means if this is the source, this is site. If this is source, this is site. How the displacement will changes. But with time, that is your UT functions. Okay, so we want to find out the unique UT for every fx0 t0. Fx0 t0 means whatever the force produce at the source. So whatever the acting at the source, based on that, we will be calculating the displacement at any point. Now, these things are computed by one phenomena. It is called a Green's function. Okay, it is called Green functions. So the thing is this: we introduce a Green function. It is called gxt. So Green function is a gxt, and that Green function is basically u at a particular earthquake or I having a distance, u at a particular position having a distance x and t. So this is the recording site or the recording part. U at a particular station location I. This will be related with the Green function between the recording station and the earthquake where it is being observed at the x0 and t0, and as a function of x and the t. So that means here it is a x0 and t0, that means at the origin, and this is the point where it is a recording site, and this is basically we are seeing that u, I, x and t. So this is related with a gxtx0. So that means this is your Green function for this point is a g, and that will be equals to your x and then comma t, because that's the time, and also with a semicolon having this is the x0 and t0 at the earthquake source location and the time. So this is what we need to calculate, which basically passes through the materials of this body, right? So Gij, so this is I, so this is your I and this is your J source, Jth source. So this is your Ith station. So Jth source, Ith station, Gij, xt, x0, t0, and with your Fj at the x0, t0. So Fj is the force which is being developed at the point x0 and t0, right? So if you multiply this one, then you can calculate this number. So you need to know, therefore, the Green function, and if you know the Green function, you can calculate the displacement at the point x and t. So is it mathematically okay? Okay, so let's see. Now, this displacement, this Green function, what will be the Green function? That if I, so what is the Green function therefore? So if your force, if this is your unity, if force is unit force, right, then whatever the displacement you observed at the site, that's the Green function between that source and site points, right? So that's the Green function for a unit displacement, unit force acted at that point. So displacement resulting from any body force distribution, compute the sum of this one. So then that will be the things. Now earthquake is usually modeled as a slip on the fault, right? So that means the fault is being slipped, and that is what the earthquake is actually all about, and the displacement is all about. This is your internal displacement, and we try to calculate the force or try to understand the force which produce the same displacement. So That is what we call it as a equivalent body force. So that means the slip on the fault is creating an earthquake, and that earthquake is recording at the recording station. So the slip on the fault, if we can express it as a fault, as a force, then that force we call it as an equivalent body force. And for that only we need to calculate the displacement part, right? So it is a equivalent body force which will be basically the slip on the fault. Okay. Now, so we need to understand what are the body forces that can occur on the inside the earth, right? So this is what we need to find it out. Now, the single force means that it will be a single force acted on a body, right? So this is a single force acted on a body. But if you have a single force acted on a body, then the thing is this, that since the system is a conserved system, so the whenever body acted on a fault, or the force acted on a fault, that force should be conserved in the momentum as well as the angular momentum, right? So both the momentum and angular momentum has to be conserved. That's the primary, the conservation of energy rules, that the momentum and the angular momentum has to be conserved. So that means due to this earthquake, the body will not rotate and till the displacement will be produces, right? So that's the part. So let's see, if we assume that there is a force like this, which is a point dipole. So that means one is acting on this side, whatever is producing the momentum, they will be producing opposite momentum. So therefore, the momentum is conserved. Yes, momentum can be conserved by, if it is a dipolar type of force, right? The force acting as a dipole separated by a distance, then it's okay. But it has been found out that this vector dipole will not explain the momentum conservation. So what we use, this will be fine, but instead of this separation, we can use the two force, and thus separation is perpendicular to the line of action of the force. So this will be forming this is what we call it, forming a couple. So two forces separated by a distance forms a couple, right? So this is what you call it as a force couple. Now force couple is fine. Force couple can explain the momentum conservation. So, but the force couple cannot explain the angular momentum conservation. So in order to preserve the angular momentum or conserve the angular momentum, we have to use a double couple. So that means this is a force couple, and then there is another things. So that means this is one couple, and then there is another couple. So these two couple, if it is being present, then the momentum will be, the angular momentum will also be conserved, right? So because one try to rotate in this way, and other will try to rotate in other way, and as a result, the double coupled force, if it's present, then that will be conserve the system, and we will be assuming that the force which is generated at the body, at the inside the source, is basically due to a double couple type of force, right? Now, this double couple force, or the force couple, it is called Mij. We represent it Mij. Okay, this Mij is the is the couple or the pair of couples which are directed in a okay. So let me write it like this way. So if these couples are directed in a I direction, ith direction. So that means this is I and this is also ith direction. So then this will be the J. This J will be the perpendicular distance, right? So this I and J, so this is equals to Mij. Mij is the moment due to a force which is directed in the ith direction and they are separated in the j direction. So this couple is producing a moment. We call it as a Mij type of moment, right? So Mij indicate the force is in I direction and they are separated in the j directions, right? So if it is a Mij, then since it's a double couple, so then there will be Mji, then that will be also present in this way. So Mji and Mij, they are basically has to be the same. So that's the part. Okay. So we have.
Can we compare something like me trying to open a bottle and use it C's? Suppose if I'm opening this tea and I'm trying to force open, cap of the bottle. So, is it like I'm getting a double? I'm not even getting even like it's simply going because even the separation, then just what that means a bond company. Because using the course, it's in another course segmented by the distance. Or is you into it, not much interested in it. Okay. It is like basically you are losing it. Then so that's done. That's the couple, but we can use it on copy so that I can end in this text in and being with us we will today in the new resolution. But if you're in the adult age, we have all to it. So then that will be make the couple make the cut straight, right? So that is a double couple type. Okay. You guess I am magnitude of it more than we will not get our couple something. And it's down the book cutting. We talk about it. But there are other non-double couple sources also to be present. So that means there are double couple, but there may be some other non-double couple forces is also present. We have to see that things also. But let us concentrate on the double couple to have a simplified version. Then we'll be seeing, if I get time, we'll be discussing about the non-double couple sources also. So the entire, because this is your earth, so that means I, J, K. So that means X, Y, and Z. So there are three coordinate axes. So we'll have several type of forces, right? So this is your one type, which is called M11, right? So that means one is in this direction and there is no separation. So M11. Then there is this is called your M12 because one direction separated by a 2. So M12, then there is M13. And so you can calculate M21 and these things, right? So these are the pictorial representation, and these all will create a moment tensors, right? So that is your M. Now, all the moments may not be present, but definitely some component of the moment in the earthquake, there will be a present, right? So if it is a impulsive sources, then all these things will be zero. Only the things are be like this, right? So then that is your only one directional type of forces, right? So that's your M0. So this is what we call it as a, so we can always have it, therefore, 6 independent elements are present, right?
So, so this is the component of the moment or the tensor of the moments which will be their presence, right? So if you can do that, then UIXT, that means whatever is the displacement at the distance x from the source, and at a time t after the earthquake has ruptured, then that will be equals to your GIJXT x0 t0 at fj, and minus there is a GXT x0, but this x0 at t0, so this x0 is basically there is a displacement, right? X0 minus displacement. So on that direction, there will be some this. So let's say, so there is a into d vector. So that is your, so x0 is the origin, and then this is your displacement, and this is your amount of displacement, and this is a vector. Since it's a vector, so this is your changes in the displacement directions into fj into x0 t0, right? So this the so we need to find out how much is the change and the due to this displacement, right? So this is the change in the green function with respect to x0, and then dik, this is your displacement part, and into fij or fj x0 t0. So this is what we need to calculate. This is one part, and this part is actually related with the moment, because that is the d into d into f. So that will be the moment value. So this is j and k. I call it as a mjk x0t. Does it make sense to everybody? So this is your distance multiplied by the force. So this is displacement multiplied by the force. So that will be the moment value. And so this is your, let me see this one. So I can write these things is like this. So this is your d, and multiplied by the force is when here. So d is in a k directions, if I can say. So this is dk, and this is your fjxt. So that means that will be, that together will be the moment values, right? So that is your moment value. So this is your dij dx0 multiplied by the moment, right? So that's, we need to find it out in case of, if I need to calculate the displacement at a particular point, right? Okay. Okay. Now, in order to do that, we need to understand what are the basic properties of the fault. And since you guys are all, most of you are all from the geology department, so you all understand these nomenclatures, right? So this is the strike of the fault. This is the deep of the fault. You understand which one is footwall, which one is hanging wall. Then there is a slip, right? So slip is the amount of displacement from one point to the other. So that's a slip value or slip vectors. And then the so this is the slip, and this angle from here, it is called the rake. On a rake angle, it is called lambda, right? And then you know what is your normal faulting, what is your reverse faulting, and the overthrust faulting, or this one. So these are all the basic definition of your fault, and this is the fee is the a strike of the right. So that is the strike. So that means it is from measured from the north, right? Okay. So this sounds to be familiar to you guys. So that's fine. So we can. So if it is a reverse fault, then the reverse fault involves the basically the compression. Okay. If it is a normal fault, this will move like so. That is your extension. So the reverse fault is in this one, and so there's a strike slip fault. There is a deep slip fault. You all know that, and then this is your lateral and left lateral, right? So if you standing on a footwall, and the other block moves to your right, then it is called right lateral shift. And if it moves to the left, then it's a left lateral things, right? So this is the strike slip. Then there are two types: left lateral and right lateral. So if you can see, it is in a moment diagram. So that means this is a one like this one, and if it is this movement, then it will be like this, right? So this is the movement of the moment diagram for the left lateral, and this is your right lateral. So both the cases, for left lateral case, the lambda is equals to 0, and for the right lateral, it is just in the opposite direction. So lambda equals to 180. Okay, so this is 180 values. Okay, and the strike can go from 0 to 360 degree with the north, and the deep can go from 0 to 90 degree, right? Because deep will be from the measure from the horizontal direction, so it will be this. Lambda can go from the 0 to 360, and the slip vector when they define as the most possible way of the slipping of the plane, right? So this you all understood, right? So based on the lambda value, this will be the lambda 0 is the strike slip fault. Lambda 180 is also strike slip, but it's a left lateral and the right lateral. So 90 degree, if it is a deep slip, but it's a reverse fault. So this is the reverse fault, and 270 degree is basically the normal faulting. So that value or that nomenclature, I should not repeat that. So if it is a right lateral movement on a vertical fault or orientation, so this is your M0 and M0, right? Because these two value, always it will be the symmetric, because M12 is same as M21, right? Because this will be always the case. So if it is M0, then this will be M0, because the motion is in this direction, right? So that is equals to M12. So that is the number here. So M0. Okay, so that is your the right lateral movement. And if, as I told you, that if it is a explosive source or the explosion occurs, then it's an isotropic things. So then all this one is there, because then all it is a M11, M21, M33. So this will be all this one. So all the diagonal element, these are called trace. Okay. So if it is a trace, then if it is a trace, then with the sum of all the diagonal element, it is called trace, and the moment tensor trace for a double couple, because then there is no moment because the forces are on the same line, so the is therefore zero, and therefore the double couple produce no volume change. So that will not change in any volume in that part. Okay, so okay, let's see. Now, this part I will not now derive for the time being, because it will take some cos and sine component calculation, XYZ direction. So you can see here there is a, so this is the fault plane. Okay, so this is the fault plane, and this fault plane has a slip vectors, right? So slip vectors is directed along this, and the angle through which through the horizon, this angle we call it as a slip angle, and this is your if it is a fault plane, then the slip vector is on the plane, right? And perpendicular to the, say suppose this is the slip, so or the fault plane, then this is the amount of slip. Then if it is the amount of the slip, then this is your slip vector d, and perpendicular to the fault, this is the normal to the fault plane. So that will be equals to your n, right? So this vector n can be written in terms of the delta, that means the dip of the fault and the strike of the fault. It is a minus sine delta sine phi minus sine delta cosine phi, and with a cosine delta, right? And if it is a t vector, so that means how the slip vector we have to write, then the slip vector will be equals to this expression, right? It is your S plus D. We can calculate that in the direction, but for the time being, you please assume this part. If it is possible, I can put the mathematics in your fault, and in your the Google Drive, all the details about how we have got these things. Okay, so now, so Mij is basically equals to your mu A into D that you have already learned. That is your the Poisson what is mu? In the formulas of the the A is the A with that. And see, so that's side area. This when unit vectors nj nij means it's basically n dot d, right? So basically it is a n dot d. So n dot d means nj d, ni dj and nj di, right? So this is your n vector dot d vectors. Okay. So so that's the part. If you can do put the I and j together, so that means if I put I equals to 1 and j equals to 1, so then this is your 2, or I equals to x. Let's see, right? I equals to x and j equals to y, and j equals to y. So if you have a both x, then this is nx dx. Means this is x and y. So then this part will be equals to nx dy plus ny dx, because this part is all with the x, then this will be all with the y, this will be all with the z, right? So then it is a x and this is also x. So then these are all nx plus nx. So this is 2nx dx. And this is x, this is y. And then you change the sign ny dx. And then this is nx dg. And then this is opposite ng dg. So then it will be this much, and all the numbers you can write it down. This will be starting with the y. So y with the x, and then then basically y with a, just you change the subscript, and then this will be the both y and y, and so on and so forth. So this is your m vector. So that will be your calculating the n dot d. So if we can express these things in terms of your northeast particle and all this component, and by taking the delta angles, so this is your MNN, MEE, MZZ, MNE, north and E. So this is because, let me tell you, if it is a vertical, and then let's see, this is your east and this is your north. Okay, so this is what is your geocentric calculation. So that means northing, easting, and the vertical. So this is your 1, 2, and 3. Whatever I was writing 1, 2, 3, and 2, right? Or might be the x, y, and z, right? So that is your, this is your x, this is your y, and this is your z. So that way we can write mxx, m11 will means n, m22 means e, m33 is the g, and then 1, 2 is ne, and so forth. And in terms of all the values, you can put it in the n and d values. We have already calculated it here. So this number you can plot, and that will pay when you can substitute with the n dot d. And let me see. So this n and d you can. So this is your x, this is y, this is your z. So this is your x, this is y, and this is z. So if you can put this number here and add them up together, and then you can find out all the M11, M0 values by using these numbers, right? So if you know the deep, lambda, and the strike of the fault, then I can calculate which moment will be generated, and that moment component we can use in the moment tensor, and we can calculate the values, right? So this is your calculation for the moment tensors. Okay. Okay. This is your the non-double coupled forces also. We'll replace these things now. We'll come back to this later. Okay. Now, let's see. What has happened? That there is a moment has been generated, and that moment is a instantaneous in the time because earthquake has moved. So with time, it has been generated a moment, right? So this moment is basically when it was 0, and all of a sudden it raised a value like this, right? So mt, so the moment function, I can model it as some sort of a Heaviside step function. This function, we call it as a Heaviside step function. So it's called Heaviside step function, right? HT is a Heaviside step function. Now, if you take the differentiation of this moment, so that means it is a rate of moment. It's a rate of moment change. So that is how the moment changes with time. Rate of moment change. So this is m dot. M dot will be just a pulse like this, right? So that is just a pulse. So if we have a earthquake, is just as a zero, then there is suddenly the force applied and the moment generate. So that is your, simply you see that it is being instantly rise and then become constant. Then your m dot will be equals to a pulse like this. Okay. So, but realistically, this is not the case. Realistically, whenever earthquake happens, the moment will be generated, but that moment will take some time to reach that values, right? So instead of a Heaviside step function, the moment function will be a ramp function. So this moment function will be a ramp function. I call it as a RT. So earthquake comes here, and then it was normal here. Then the moment will be generated, but the moment instantly do not rise. It will rise after some times, and then it's constant, right? So this is what we call it as a rise time, right? So this is what we call it as a rise time. So that much time it will reach to take it as a constant values. So if I do a m dot t, so this means time derivative of this function, then this time derivative of the function will be a box function, right? So if you take this time derivative, so that means it will rise, then it will be this, and then it will be 0. So this tau is equals to this one, right? So this tau is the width of the box, right? So this is equals to your BT. Now the area under the boxcar function, if we can say this is your area, so this is your m dot into dt. So this is your m into tau. So that is what we call it as a m0. So that is your moment or m0 values. Okay. So this is the particle dislocation theory. So that's your m0 values, and we will be seeing how this m0 will create the time history at the recording site. Okay. Thank you. Only take